In the early 20th century, the Golden Gate Strait presented one of the planet's most formidable engineering puzzles. Here, the Pacific Ocean surges into San Francisco Bay, creating turbulent currents, relentless winds, and dense, chilling fog that could descend without warning. For decades, the idea of bridging this mile-wide chasm was deemed an impossible feat, a quixotic dream challenged by nature itself. The sheer scale of the environment meant that any structure would face forces unprecedented in bridge design, demanding a monumental leap in engineering thought and execution. Amidst this daunting backdrop, an ambitious engineer named Joseph Strauss emerged. Having built hundreds of bridges, though none approaching this scale, Strauss believed he could tame the strait. His initial designs were controversial, leaning towards a cantilever suspension hybrid that many found inelegant and impractical. Yet, his unwavering determination and relentless advocacy for the project gathered momentum, fueling public imagination and eventually securing the necessary funding to proceed. He was a force of will, ready to challenge the status quo, though perhaps not yet fully grasping the structural complexities ahead. The engineering landscape of the 1930s presented a stark reality. No bridge had ever attempted a main span of 4,200 feet, let alone in such an unforgiving environment. Existing suspension bridge theories were not robust enough for the colossal forces at play. Engineers faced fundamental questions about stability, material stress, and aerodynamic response. This wasn't merely about building a longer bridge, it was about inventing new ways to understand and predict structural behavior, pushing the very boundaries of physics and materials science to create a structure that could defy gravity, wind, and seismic shock. Behind Strauss's public persona worked the true intellectual architect of the bridge's design, Charles Alton Ellis. A brilliant mathematician and professor, Ellis dedicated years to the intricate calculations, often working 14-hour days, 7 days a week. He meticulously translated Strauss's vision into an elegant, structurally sound suspension bridge, creating 10 volumes of complex computations. His expertise in advanced structural analysis was indispensable, yet his quiet, academic nature often left him in the shadow of the more flamboyant Strauss. Ellis was the quiet backbone of the project's technical triumph. Ellis did not work in isolation. He collaborated closely with Leon Moisseiff, a renowned consulting engineer whose pioneering deflection theory revolutionized suspension bridge design. Moisseiff's theory posited that the bridge deck itself contributed significantly to the structure's rigidity, distributing forces more evenly and allowing for more slender, yet stronger, designs. This was critical for the Golden Gate, enabling it to flex and sway under immense loads without failing. Moisseiff's insights, applied by Ellis, transformed the bridge from a static structure into a dynamic system interacting with its environment. San Francisco's infamous winds, routinely exceeding 60 miles per hour and capable of gusts over 100 miles per hour, posed an existential threat to any bridge spanning the strait. The design team had to account for dynamic wind loads, aeroelastic flutter, and vortex shedding phenomena not fully understood at the time. They incorporated a flexible, open-truss roadway design and robust tower construction to allow the bridge to breathe with the wind, rather than rigidly resist it. This innovative approach was crucial, ensuring the bridge would not succumb to the same fate as later, less aerodynamically sound designs. Beyond wind, the strait presented other formidable natural adversaries. The powerful tidal currents, among the strongest in the world, churned relentlessly, complicating any underwater work. Dense, persistent fog frequently reduced visibility to mere feet, making construction at height extremely hazardous. These conditions demanded not only robust engineering solutions but also incredible human resilience and ingenuity. Divers working in near-zero visibility, steelworkers contending with slippery girders veiled in mist, every aspect of construction was a battle against the elements, pushing the limits of human endurance and technical adaptation. Building in earthquake-prone California added another layer of complexity. The Golden Gate Bridge had to be designed to withstand significant seismic activity, a challenge compounded by its massive scale. Engineers understood that flexibility, rather than rigid strength, was key. The towers were designed to sway independently, and expansion joints were incorporated throughout the deck to absorb movement. This foresight, a testament to the team's comprehensive approach, ensured that the bridge could endure the tremors of the San Andreas Fault, a critical feature for its long-term survival in a seismic zone. One of the most heroic and dangerous phases of construction involved the South Pier Foundation. In a colossal engineering feat, a massive cofferdam and open-bottomed caisson was sunk through 65 feet of swirling, powerful currents to bedrock, 100 feet below the surface. Workers battled not only the immense pressure and freezing temperatures but also the risk of rogue ships. This underwater operation was unprecedented in scale and difficulty, demanding precision and courage from the crews who built a stable foundation against the raw power of the Pacific Ocean, anchoring the bridge firmly to the earth. From these monumental foundations rose the Golden Gate's iconic towers. Standing 746 feet tall, they were the tallest structures west of New York City at the time of their construction. Fabricated from over 600,000 rivets and weighing 44,000 tons each, these steel giants were built section by section, defying gravity and the relentless winds. Crafting these immense structures required steelworkers to operate at dizzying heights, often in thick fog, meticulously assembling each piece. Their construction was a testament to the precision, bravery, and sheer physical endurance of the human workforce. As the project progressed, tensions between Joseph Strauss and Charles Alton Ellis escalated. Strauss, desiring sole credit and perhaps frustrated by Ellis's academic pace, dismissed his lead design engineer in 1931 without official recognition or compensation for his extensive work. Ellis, heartbroken, continued to work on the calculations in his spare time, driven by a commitment to the bridge's success, even as his contributions were systematically erased from official records. This episode remains a poignant reminder of the human cost and political machinations behind grand achievements, and how genius can be tragically overlooked. With the towers complete, the next monumental task was spinning the main cables. This revolutionary technique involved a synchronized dance of specialized spinning wheels carrying individual wires back and forth across the strait, high above the water. Each wire was precisely laid, one by one, gradually accumulating into massive bundles. It was a painstaking, continuous process, demonstrating an incredible feat of coordinated engineering and machinery. This method, perfected on earlier bridges, was applied here on an unprecedented scale, literally weaving the bridge's strength into existence, wire by delicate wire. The resulting cables were marvels of engineering. Each of the two main suspension cables measures a colossal 36 inches in diameter. Within these two immense structures, an astonishing 27,572 individual galvanized steel wires were meticulously spun and compacted. Laid end to end, these wires would stretch for approximately 80,000 miles, enough to circle the Earth more than 3 times. This incredible network of steel provided the primary support for the entire bridge, capable of bearing immense loads and withstanding the relentless environmental forces of the Golden Gate. In an era when workers' safety often took a backseat to progress, Joseph Strauss made a groundbreaking commitment. He insisted on the installation of a massive safety net, stretched beneath the bridge's deck during construction. Costing an additional $130,000, this innovative measure was initially met with skepticism and even derision by some. However, its effectiveness soon became undeniable. It was a revolutionary safety protocol that set new standards for large-scale construction, prioritizing human life over mere economic expediency, a testament to a shift in construction ethics. The safety net proved invaluable, saving the lives of 19 workers who fell from the dizzying heights of the bridge structure. These men, who literally cheated death, became known as members of the exclusive and grimly named Halfway to Hell Club. Their survival stories underscore the constant peril faced by the construction crews. The net transformed what would have been certain fatalities into minor injuries, allowing these skilled workers to return to the job. It's a powerful symbol of how human ingenuity, focused on protection, can mitigate the inherent dangers of such ambitious projects. The Golden Gate Bridge wasn't just an engineering marvel, it was a beacon of hope during one of America's darkest periods. Constructed between 1933 and 1937, amidst the throes of the Great Depression, the project provided thousands of jobs at a critical time, offering employment and purpose when both were scarce. Its construction became a powerful symbol of human resilience and collective determination, demonstrating that even in economic despair, grand visions could be realized. It boosted national morale and represented a bold investment in the nation's future, inspiring a generation. After 4 intense years of construction, battling nature, overcoming technical challenges, and personal rivalries, the Golden Gate Bridge finally opened to the public on May 27, 1937. It was a moment of profound triumph, marked by a pedestrian day where 200,000 people crossed the span. The bridge immediately captured the world's imagination, not just for its monumental size and striking beauty, but as a testament to humanity's ability to conquer seemingly insurmountable obstacles. It stood, and still stands, as a proud declaration of American ingenuity and perseverance. Decades later, the Golden Gate Bridge continues to stand as a testament to the foresight and brilliance of its engineers. Its structural integrity has gracefully endured countless storms, high winds, and seismic events, proving the unparalleled robustness of its design. The innovative use of deflection theory, the meticulous cable spinning, and the sheer scale of its foundations laid the groundwork for future suspension bridges worldwide. It is more than just a crossing, it's an active, living monument to pushing the boundaries of what's possible, inspiring engineers and dreamers alike. The Golden Gate Bridge remains a symbol of technical achievement, but it also embodies the complex human story behind its creation. While Joseph Strauss took much of the public credit, it's crucial to remember the immense contributions of individuals like Charles Alton Ellis, whose calculations formed its very backbone, and Leon Moisseiff, whose theories enabled its elegant flexibility. Their combined genius, alongside the courage of thousands of workers, transformed a perilous strait into a pathway, and an impossible dream into an iconic reality. The bridge stands as a permanent tribute to the collective power of human expertise and vision.